This is the UDU method for solving integrals. This is another Mulberry day because this may be the very most important section of the entire year. This is going to tremendously expand upon the amount of things that we can take the integral of, just like the chain rule expanded upon the number of things you could take the derivative of. This is a very powerful technique that we're going to use pretty much every single day the rest of the year. This is also a technique that is going to be easy for everybody. Some of us will think it's easy after the very first example. Some of us will need a couple of assignments to practice this stuff to make sure it's easy for us. But trust me, when we get to like the next chapter and 3 chapters from now, if you come up to me with a question when we're learning these harder integral techniques, and I'll just say to you, hey, that's a UDU problem right there, you'll be like, nope, say no more, and you'll just go back and you'll just do that problem because you automatically will know how to do it. So once you recognize it's a UDU problem, this will be a pretty easy technique for everybody. So really important day though, really important section. That's when we got the mulberry color up in here. When we do this, when we first learn the steps, first of all, this is going to be a 2-part video. I'm going to show you all the normal problems in this first video, and then the part 2 video is going to show all the trig examples. Some of us will only have questions over the trig examples, partially because we don't know the trig derivatives as well as we should. So we'll review all of that in the second video there. So if you just want some trig examples, watch the second video over UDU. But here are the steps that we're going to follow. Eventually, once we do a few examples, you won't need to look at these steps at all. But essentially, we're going to take a couple of integrals that we don't know how to integrate at this point, and we're going to substitute u's into the problem. We're going to essentially turn it into something that we can integrate with the u's. We got to be careful with our numbers and balancing things. And then once you get the u's in the problem, you're going to integrate it, and then we'll plug the x's back in. So that's what we're going to do. We're going to take harder looking integrals, substitute u's in the problem, and then integrate that, and then substitute the x's back into the problem right there. The very first couple of problems here, don't worry about why I'm choosing u. I'm just going to show you the nuts and bolts of the problems, the details of the steps. And then we'll, after we work out a few examples, then I'll talk about why I chose that for the u, and we'll put that on our little tendency list right here. So here's first example there. So when I see this, don't worry about y yet, but I'm just going to choose u equals the inside of that radical, that x cubed plus 1 part. So I chose the u, and then here's what we're going to do now. We're going to find the u. That means we're going to take the derivative of this. So we're going to go du equals, just take the easy derivative, multiply with the power, decrease the power by 1, and then we'll tag on the little dx right there. Technically, it's du over dx equals that, and then we multiply both sides by the dx, but this is going to be helpful for us with the notation, with all the different letters that we'll work with throughout the year. So here's what we need to notice. When you take this derivative on a UDU problem, what we should notice is something is going to match up here. So notice what matches up. I got an x squared dx, and right here I have an x squared dx. I'm going to put down, I'm going to call those the squiggled part of the problem. So those are the squiggles that are matched up. And if I ask you what is extra, this 3 is extra. Now, if you have an extra number, that's really good, okay? If you have an extra letter, that's no good, all right? Either you chose wrong for u, or it's not a UDU problem right there. So we'll talk about those. But if you have an extra number, it's very easy to handle the extra number. So here's what we're going to do. I'm going to rewrite this integral using u's, all right? So once you get your squiggles matched up, I'm going to tell you, once the squiggles are matched up, that part of the problem is handled. It's done, all right? You don't have to worry about it, okay? So the squiggle part is going to be handled. So we're going to just, here's what we're going to do with the numbers. I got, when we rewrite the integrals, you're going to balance the numbers. Balance the numbers always with the reciprocal. So if you have an extra 3, we're going to balance that with the reciprocal with the 1/3. And what I'm going to tell you, the squiggle part is handled, so I'm not worried about that stuff anymore. I'm just going to substitute for the rest of the part. So instead of having the square root of that x cubed plus 1, my u is equal to that inside that square root. So I'm just going to have the square root of u, and then I'm going to tag on the du. So again, I had the square root of that x cubed plus 1. All I did was plug in the u, since the x cubed plus 1 is equivalent to u, and I got that in terms of u. All right, so that's what we're going to do. The squiggle part is handled. You're going to substitute in the u's for the rest of it, and then you always tag on the du. At this point, you should not have any x's in the problem. If you do, something is wrong. We chose wrong for the u. We got to go, our derivative is wrong. We got to go back and we need to fix that. Now, some of you might be wondering what happened to the squiggle part. Okay, what I'm going to tell you what happened to the squiggle part, it's built inside that du. That's the squiggle part. See, it's built inside there, but the du also had that extra 3, which is why we put that 1/3 out there to balance that, just to prove it to you. I'm not going to do this every single problem, but let's just go over to the side here a little bit. If I go to this problem here and I go ahead and plug the x's back in, so the 1/3 is just there, right? And then if I plug all the x's back in, that becomes the square root. I plug in that x cubed plus 1. And if you do substitution, like when I plug in that 3x squared dx in place for the du, like instead of the du, I write down what the du is equal to, that 3x squared dx, right? And then look, that's why we needed that 1/3 out there, because now those 3's cancel out, and this stuff right here is your original integral right there. So I just wanted to prove that to you, that it is equivalent to the original integral. I didn't change the problem at all, and that's why we needed that extra 1/3 out there, because the du had that extra 3 built inside there, and right there, that's not your original problem. But when I put that 1/3 out there and those 3's cancel out, there's our original problem. All right, so that'll sink in. That'll get easier and easier for you. But once you see that step, that's really the hardest part. And now we're just going to integrate this. So now we have something we can integrate. So this is the integral of u to the 1/2. And so we know when we integrate that, we're going to get u to the 3/2. You add 1 to that power, and then you divide it by the same thing. And remember, when you divide it by 3/2, that's the same thing as multiplying by the reciprocal right there. And then this 1/3 will just carry down. And so here's going to be our final answer. We're going to get 2/9. And then for the final step, so notice that I rewrote it and I integrated it. And then your final step is you're just going to plug the x's back into the problem. And then it's an indefinite integral, so we always have the plus c right there. So I'm going to take the u equals x cubed plus 1, plug that in place for the u. And then you need to remember that 3/2 power right there. And then you got your plus c, and then you're done. And then we're not going to do this on every single problem, but just because it's a brand new integral technique, remember what our integral answer is. If I take the derivative of this answer, I should get that original problem. So let's just do that real quick. If I take the derivative of this, I'm going to multiply by the power. So if I take 2/9 times a 3/2, the 2's cancel out, 3/9 gives me 1/3. And then I'm going to leave that inside alone. I'm going to decrease that power by 1. And then I'm going to remember to times it by the derivative of the inside, which is this 3x squared. Notice that these 3's cancel out, and I have the x squared. I have times the square root of that x cubed plus 1, and that is the original integral right there. So it does work. We're not going to do that on every single problem. I might do that on a trig example there, but we're just going to kind of trust that process kind of works it. But you could check that if you wanted to right there. All right, so there's our steps. My guess is once you do a couple of these, get a couple under your belt, you won't really need to look at those steps too often. Sometimes we just make balancing mistakes, our derivatives off a little bit, or we forget to balance the numbers there. So those mistakes always go away as we practice more and more. All right, so let's do a couple other examples with that. So another integral, brand new problem. And this time I'm gonna let u equal, don't worry about y yet, but I'm just gonna let u equal the inside of that square root, that x squared plus 1. And then I'm gonna go through the steps. So I chose u. Next thing we're gonna do is find du, which is a simple 2x, tag on the dx there. And I'm gonna look for things to match up, and I'm gonna do the squiggles right here. So if I have an x dx right there I have an x dx right there. If I had a 2x dx on the top, well then everything will be squiggled, everything will be matched up. There's nothing extra, so there's nothing to balance. But right here I have the x dx to match up, that's good. And I have just an extra number. If I have an extra number, that's good. If I have an extra variable, I screwed something up there. I gotta choose something different for u, or it's not a u du problem there and I gotta do something else there. But if you have an extra number and that 2 isn't part of it, then you balance the extra numbers with the reciprocal. So if we balance the 2, you're going to balance that with a 1/2. And then be careful here. So the squiggled part I'm telling you is handled. That part is handled, and we're going to substitute for the rest of it, okay? So the rest of it, since it's on the bottom, we need to put a 1/, and instead of the square root of those x's, the u is equal to that inside of that square root. So it's 1/, the square root of u, and then you always tag on that du. And again, just to prove it to you one more time, I don't need you doing this every single time, but at the beginning here, you got the 1/2 there. And then if I plug the x's back in, you got 1/, the square root of that x squared plus 1. And then if you plug in what the du is equal to, that's equal to that 2x dx. And then those 2's cancel out, and notice that you got your x over that square root. So it's the same thing right there. But I don't need us to be doing that every single time there. It's just trust that that process is going to work there. The squiggle part is in there, it's built inside there. It also had an extra number, so we balance that with the reciprocal right there. And then notice that we have something we can integrate. This is u to the negative 1/2. So when I integrate u to the negative 1/2, that's going to be u to the positive 1/2. But then you're going to divide it by 1/2, which means you're going to times it by the 2/1. This 1/2 is just out there. That carries down. And then those twos cancel out. So we get the square root of u. And then you got to plug the x's back into the problem there. So your u is equal to that x squared plus 1. Just substitute the x's back into the problem. And then since you did an indefinite integral, you got to remember to tag on the plus c, and then you're done. Let's do one more example like that. All right, so as I look at this, you probably, hopefully already kind of recognize that on this problem here, if I say what the u is equal to, hopefully you're thinking, got a natural gut instinct there that the u is going to be the inside of that parentheses right there. And then when we take the derivative, so we're going to go du, just multiply by the power, decrease the power by 1. And then we're going to look for things matching up right here. So I have an x squared dx right here. I have an x squared dx right there. And then, so the squiggles are the variable parts matching up, and then the number is just extra. And again, if I had a 3x squared in front, then the 3x squared would be squiggled, the whole 3x squared would be squiggled. There would be no need to balance any numbers there. You would just go straight to the inside of that part there. But since you have an extra 3 inside that du, you're going to balance that with the reciprocal. And then I'm telling you, the squiggled part is already handled. You ain't got to worry about that. That's done. Just substitute for the rest of it. Since your u is equal to the inside of that parentheses, and now we simply have a u to the 80th power. And then you got the du. So if that was like an x cubed plus 5 squared, I could easily just multiply that all out and use my easy power rules when I integrate that stuff. But if you go to the 80th power, you're not going to have that option. So now that you got an easy u to the 80th power, now you just integrate this like normal and add 1 to that power, divide it by that same power, carry down the 1/3, and then we're going to plug the x's back in. So we're going to get x cubed plus 5 to the 81st, and then 3 times the 81 is going to be 243, and then you can tag on that plus c. And I don't care if you write the problem like that. Up here, you can put it as x squared plus 1 to the 1/2. Right here, you could write this as 1/243. Like that. I don't care through the whole year. Those are equivalent problems right there. So just integrate it, plug your x's back in, and it's an indefinite integral, plug in the plus c. And on the definite integrals, we could plug those numbers in place for x and get a number for that. So there's 3 examples of like what I say, like the normal type problems there. Now, there's not one magical thing that I can tell you to always choose this for you, but there are tendencies, there are normal things that you could try that I want you to always think about in your head first. Typically, if we're trying the wrong things not on this list, we're making it way too complicated and we're gonna mess that up. You gotta think simple first, and you gotta try normal, simple tendencies first before you get too crazy with it. There's some crazier problems out there, and we'll have to adjust some things sometimes there, but most of the time, if you stick with what we're talking about right here, you're gonna be just fine there, okay? So on our tendency list, this is just methods for choosing u. You might wanna, we'll just jot down a couple things there. Look back at why we chose that for the u. So what we typically did, like I said, this is something that always works. This is something that works most of the time. But one thing that we did, we chose the inside of the parentheses, or what was underneath the square root. Okay, so that worked on a couple of those problems there. Also, what we chose was the u is typically the stuff with the higher power. And that makes sense. If I let u equal the x squared and I do the du of that is going to be a 2x. You're not going to match up an x cubed from that, right? So if you let the u equal the stuff with the higher power, then your du is going to give you that lower power to kind of match up with there. And so you just let it equal the inside the parentheses, because if you have a u to the 80th power instead of like a binomial raised to the 80th power, that's what we want to get. We can handle that 80th power no problem, but we just want to get a single thing in right there. So those are just some normal tendencies that we're going to choose on the normal problems. The inside the square roots, the underneath the parentheses, underneath the radicals, and stuff with the higher exponents right there. We're going to have a couple different things to jot down with the trig. That's going to be in the second video. The second video is just trig examples only. So if you need a refresher with that, then you could just do that, and then we'll have a couple things for that. And then before I forget, those are your 3 Pythagorean identities that we got to make sure we know. And I want to mention, not every integral will be a u-du substitution, all right? And even in your homework for this time, this is not a u-du problem right there. This is this you see a monomial in that denominator. You could do a that over that and that over that problem, turn it into that, and then integrate each piece separately right there. So you add 1 to the exponent divided by that same number, and then multiply by the reciprocal right there. So that's just a normal problem with our easy power rule there. Just kind of keep that in mind. And not everything is going to be a u-du, but most of this stuff will be a u-du, and we just want to practice this as much as possible. All right, so tune into the second part of the video for the u-du. Next video, u-du, nothing but trig examples there. So if we, the reason for that is if you just need a trig refresher, then you could just watch that one video instead of watching the whole thing. All right, practice this stuff, really important. It will be easy. Practice it and then ask me questions. We'll make sure we're good there.